Have the bytecode, you can run it on the JVM. If you want to run it on Windows, you'd be making use of the Windows JVM. The Windows JVM would convert the bytecode into executable instructions on Windows. The executable instructions on a specific operating system typically are called machine code. The CPU or the computer at the end understands only zeros and ones. So your bytecode will be converted into zeros and ones by the JVM. On Windows, the job is done by the Windows JVM. On Unix, you have a separate Unix JVM. On Linux, you have a JVM as well. So Java achieves platform independence by having separate JVMs for each platforms. This ensures that your first steps remain the same. Your output from any Java project is compiled Java code or the bytecode. Once you have that bytecode, once you have the jar file or the class file with you, you can run it on any operating system. One thing you would observe is that this is little different from languages which are earlier to Java. Examples are C and C++. C and C++ are not platform independent. If you are having C or C++ programs, you need to compile them separately for each operating system. How does it work for C and C++? C and C++ are compiled languages. Once you have C or C++ code, you can compile it and you directly get the machine code. So if you use a Windows compiler for C or C++, you would get Windows machine code as the output or a Windows executable as an output. So for C and C++, if you want to run the code on different operating systems, you would need to make use of different compilers and create different output files. So if you want to run your C program on Windows, you need to first use Windows compiler to compile it, and then you'd be able to run it. Similarly, if you want to run it on Linux, you need to compile it using a Linux compiler. So platform independence is the ability of a software to run on different operating systems without changes. We saw that compiled Java code or the bytecode can run on any operating system because of the JVM. However, in languages like C and C++, you need to recompile your code separately for every operating system. Welcome back. In this video, let's talk about platform independence versus portability. These are very similar terms, but there is a small difference between them. Let's try and identify what the difference is in this specific step. What is platform independence? Ability of a software to run on different operating systems without modification. Java compiles to bytecode, which can run on any JVM. So a Java program compiled on Windows can run on Linux or Mac OS without recompilation. So Java follows write once and run anywhere. Now, what is portability? Portability is the ability of a software to be adapted to different platforms with minor changes. So if you have a piece of software where you can make minor changes, maybe a recompilation or small modification in source code, and you'll be able to run it on a different operating system or a different platform, that's when you call the software to be portable. So if your software is platform independent, it should run as is on different operating systems. If your software is portable, then small changes are allowed. You can make minor changes and run the software on different platforms. A good example is a C or C++ program. Once you have C or C++ program, it can be run on different operating systems if you do separate compilations for each of the operating systems. So C and C++ are portable but not platform dependent. So what we are talking about is the fact that Java is both portable and platform independent. With Java, you don't really need to make any changes to the compiled code to be able to run it on different operating systems. So it's both platform independent and portable. However, when it comes to C and C++, you need to make small changes. You need to be able to compile the code again before you'd be able to run it on different operating systems. So C and C++ need minor changes before you'd be able to run them on. So C and C++ programs need minor changes before you'd be able to run them on different platforms. That's why they are portable, but they are not platform independent. Assembly language also can be used to write programs. When you are writing assembly language programs, you are using instructions or mnemonics. These instructions are specific to a specific platform. So whenever you write an assembly language program, it is specific to a particular platform. Whenever you want to write the same program for a different platform, you need to completely rewrite it. And that's why programs which are written in assembly language are neither portable nor platform independent. A little later, we'll be discussing a little bit more about assembly language. In this quick step, we discuss the difference between portability and platform independence. If you are able to run a software as is on different operating systems, different platforms, then it's called platform independence. If you need to make small changes and then you'll be able to run the software on different platforms, that's what is called portability. In this step, let's talk about the difference between source code or code, machine code and bytecode. What is source code? Source code is nothing but human readable instructions written in a programming language. This is an example Java program. You are an expert on Java, so this should be very, very simple program for you to understand. So you have a Java program in here. Now you'd want to execute this. If you want to execute it, you need to convert this into machine code before you'd be able to run it on a specific operating system. Now, next we go to bytecode. Bytecode is something which is specific to JVM or Java. Bytecode is an intermediate platform independent code which can be executed by a Java virtual machine. Bytecode runs on the Java virtual machine. Java virtual machine converts the bytecode into machine code for the specific operating system. Bytecode looks something like this. So over here we are loading hello world, and then we are invoking a method and we are returning back. What you are seeing in here is bytecode. So whatever program that we have in here, when you compile it, when you do javac hello.java, what is the output inside the class file? This is what would be present. This is the bytecode which would be present. The JVM can take this bytecode and run it on any specific operating system. Next, let's get to machine code. What is machine code? Machine code is the final data class file which contains bytecode, and then you'd be able to convert your bytecode into machine code. Who does that? That's done by the JVM. JVM is the thing which converts your bytecode into code that can run on a specific operating system. Welcome back. In this video, let's talk about the major events in programming history that led to Java. There are a lot of key events that happened in the programming world in the last few decades. Here are a few that I think are really, really important. Earlier, we talked about the fact that whenever you'd want to run some piece of code on your machine, what we would do is we would write source code, and the source code needs to be finally converted into machine code before you'd be able to run it. There are a lot of key events that happen in the programming world. So whatever code you write, C code or Java code, it needs to be converted into zeros and ones before you'd be able to run it on the operating system. The first two events in here are related to writing things which are very, very close to machine code. The first one is writing machine code, which is writing code in zeros and ones. The second one is using assembly language. This is where you would write few mnemonics, few instructions. And these instructions are very, very near to the binary code as well. So the first two approaches are things which are really, really near to machine code approach. First programs that were written, just small program collection. Java is used to build web applications, REST API, microservices between JDK, JVM, and the JRE. At a high level, the hierarchy is something like this. JDK, or the Java Development Kit, contains the JRE, or the Java Runtime Environment, which contains the JVM, or the Java Virtual Machine. So let's get started from the JVM. So let's go to the bottom and get started with the JVM. So what does the JVM do? JVM is the Java virtual machine. It's a virtual machine that can interpret or compile your Java bytecode into machine code for execution. Whenever you write Java program, if you want to share it with somebody, you would compile it. You would create a class file or a jar file, and you would share it with others. And if you want to run this Java bytecode, you would need a Java virtual machine. So the job of the Java virtual machine is to efficiently run your Java bytecode. There are different JVMs for different operating systems. Why? Because the machine code for different operating systems is different. So you have Windows JVM, which can convert bytecode to Windows machine code. You have Unix JVM, which can convert bytecode to Unix machine code. So you have specific JVMs for different operating systems, and these JVMs can convert the bytecode into machine code for that specific operating system and execute it. Now, what are the different things that are part of the JVM? Number one is the class loader. Your Java class files need to be loaded into memory before they can be executed. That's the job of the class loader. There is also bytecode interpreter. The bytecode needs to be converted into native machine code. That's the job of bytecode interpreter. You'd also want to optimize the execution of your bytecode. You'd also want to optimize the performance. Typically, interpreting is very slow because interpretation is done line by line. If you do things line by line, you will have bad performance. That's where JVM brings in. If you do things, you want to share it with somebody, just-in-time compiler. Just-in-time compiler optimizes performance by compiling frequently used bytecode into native machine code. Just-in-time compiler can identify hotspots in code, that's basically frequently used bytecode, and it will be converting it into native machine code. It will be caching it and reusing it instead of reinterpreting it each time. So what we are talking about is the fact that JVM contains everything to be able to execute your Java bytecode efficiently. It has a class loader, it has a bytecode interpreter, and a just-in-time compiler. Now, if you want to run a Java program, is JVM sufficient? Nope. You'd need other core Java libraries. You'd need classes like string, which are present in java.lang. You'd want collections, which are present in java.util. How do you get access to all of them? That's where you need JRE, or the Java Runtime Environment. Java Runtime Environment is a package that provides everything you need to run Java applications. but it does not include development tools. If you want to compile Java code, you cannot do that using a JRE. JRE only allows you to run Java applications. What does JRE include? It includes everything that the JVM includes. And in addition, it also has the core Java libraries, all the essential Java classes that we will typically make use of in our Java programs. All of them are present as part of your JRE. So if you'd want to run it, that's when you can go for JR code or Scala code or group. That's where the system path. So if the boots, very, very important, multiplied by 2 with 100.
Last week on the channel. All right, before this video gets started, I just want to make one thing clear. I'm not
Welcome to what we believe is the world's best Java applications. I've been using collections framework for more than 2 decades right now. And I would say Java creators have done a great job in designing the collections framework. They did not only do a good job while creating it, but also they ensured that the collection framework evolved over a period of time. We had generics which were introduced, and collection framework was updated to make use of generics. You can use enhanced for loop around all collections. And in addition to synchronized collections, Java 5 introduced concurrent collections like concurrent hash map. Java 8 is my favorite Java new release. In Java 8, one of my favorite features was introduced: functional programming. Streams, lambda expressions, all of these were introduced in Java 8. In Java 8, collections framework also was enhanced to enable functional programming. In Java 9, factory methods were added to create immutable collections. You can use list.off or set.off or map.off to be able to create immutable collections. And in Java 21, sequenced collections were added to ensure consistent ordering across different types. We will discuss a lot more about these features as we go further in this specific section. In the first version of Java, the collection classes or the classes which were present to group objects did not have a proper design. There were no consistent set of interfaces. Collection framework was introduced in Java 1.2. And as we saw, collections framework kept evolving with different versions of Java. In this step, let's talk about the need for collections. Why are collections needed? Collections provide a flexible and efficient way to store, retrieve, and manipulate data. Let's say I have a set of numbers to store. One of the options that I can make use of is an array. But arrays have a lot of limitations. Arrays have a fixed size. They cannot grow or shrink dynamically. In array, you need to add in a lot of manual operations. If you want to search for a number, or if you want to add a new number, or if you want to remove a number from the middle of an array, you need to write all the logic for it. And also, if you want to do things like sorting, searching, or if you want to implement advanced data structures, you would need to do all the work. There are no built-in methods for it. So what we are talking about is the fact that if you'd want to create an array and perform operations on it, you would need to write a lot of logic. Another problem is that arrays have fixed size in Java. Let's say you have created an array of strings of size 3. If you want to add a new name after adding in 3 elements, you need to create a new array. That's where collections framework comes in. How does collection framework help you to solve this problem? Collections framework allows dynamic resizing. Each of the collections can grow or shrink as needed. There are predefined methods to support adding, removing, sorting, and searching elements easily. And you get a rich set of data structures, lists, set, map, queues for different needs. So if you are creating an array list, you can dynamically add elements. You don't need to manually resize it. In this step, we quickly discuss the need for collections. In this step, let's get a 10,000 feet overview of the interfaces in the collection framework. There are a lot of interfaces in the collection framework. What we are doing now is we are discussing the most important ones. At the root of the collection framework is an interface called collection. It has methods like add element, remove element, and a lot of other operations. Sequenced collection inherits from collection interface and adds in a well-defined order. You can add an element at the first, or you can add an element at the end, or you can remove the element at the end. So sequenced collection defines an order for the elements. List stores ordered elements, it allows duplicates, and it supports index. So in a list, you can say add first, add last, or you can say I would want to add an element at a specific Windows compiler to compile index. So I can say I would want to add element E at an index 3. So list stores ordered elements in an ordered way. You can say I would want to have this element at this specific location. It allows duplicates. You can add the same element twice, and it supports indexing. Set interface represents a collection having unique elements only. No duplicates are allowed. In a sorted set, you maintain the unique elements in an sorted order. In the navigable set, you would add search and navigation methods. You can say things like, I would want to find all elements which are less than a specific element or greater than a specific element, and things like that. So set stores unique elements. Sorted set maintains the unique elements in a sorted order. Navigable set adds search or navigation methods around the elements. Next is the queue interface. What happens in a queue typically? If you are standing in a queue, the first person who arrived into the queue first is the one who will be served first. So it's first in, first out. Whoever comes last will be served last. So in a queue, the element which came first is processed first. Queue provides a collection representing FIFO, first in first out processing of elements. Double-ended queue, DQ, is a double-ended queue. Basically, you can perform operations at both ends of a queue. You can add an element at the start of the queue or at the end of the queue. You can pick up an element and process it from either the start of the queue or end of the queue. So you can process things from both the ends. That is what is called DQ or double-ended queue. So what we are looking at is the fact that collection is the root. You have sequence collection which adds an order. List stores elements in an ordered way and it supports an index. Set stores unique elements. Queue is used for FIFO processing of elements, and double-ended queue allows you to process elements at both ends of the queue. These are all extensions of the collection interface. All the interfaces which we have highlighted in here are extensions of the collection interface. There are also interfaces which are present in the collection framework which don't directly inherit from the collection interface. And one of the most important ones is the map interface. In a map, you would store key value pairs. So you would say, I want to store this key and the value for this specific key should be this. So key value pairs are stored in a map, and in a map, keys must be unique. It's very, very important to remember that the map interface does not inherit from the collection interface. In the set interface, we talked about sorted set and navigable set. Similar to that, in the map interface, you have sorted map, which represents elements which are stored in sorted order. All the keys are stored in a sorted order. Navigable map adds search or navigation methods. If you have a map, you can say, I would want to find all the keys which are greater than a specific key. Or you can say, I would want to find all the elements which have keys less than a specific value. All those kind of operations are supported by navigable map. In this step, we got a 10,000 feet overview of the important interfaces in the collection framework. Let's dig deeper into some of these collections in the next steps. I'm sure you're having a great time, and I'll see you in the next step. What are the key methods in the collection interface? As we talked earlier, collection is the root interface of the collection framework. The collection interface defines a number of methods. Let's look at some of the important ones. Add an element, adds an element to the collection. Remove an element, removes an element from the collection. Size returns the number of elements in the collection. Is empty, is the collection empty or not? Clear removes all elements from the collection. Contains checks if an element exists in a collection. Contains all, you can pass in any collection and you can check if all the elements in this specific collection exist inside the current collection. Add all and pass in a collection. Add all elements from another collection. Remove all matching elements. So we are sending a collection. Whatever elements match with the elements in this specific collection, they would all be removed. Retain all, and you are passing in a collection. Keeps only elements which are present in another. Whatever elements are present in this specific collection,